Suppose we are given a number which has the following decimal expansion. It is 2.3 and then 17 repeated. So it's 2.3, 17, 17, 17, and so on. And our task is to write it as an irreducible fraction. So you may know already that a periodic decimal number necessarily corresponds to a rational number. So if the decimal expansion of a number is periodic, then such a number can be represented as a ratio of two integers. It's a rational number. And so we're going to see why that is the case in this question. So we're given this number, so we're going to write it as a series. We'll write 2.3, 17 repeated as 2.3 plus 17 over 1000 plus 17 over 10 to the fifth. So you see what I'm doing here is the first term captures the first occurrence of 17 in this expansion. The second term corresponds to the second occurrence, and so on. Then I'll have 17 over 10 to the seventh, etc. What is the moral of this? Well, you see that this expression is clearly not a geometric series because the ratio of the second term to the first term is quite different from that of the third term to the second term. Now, what this is, however, it is a sum of a number, 2.3, and a geometric series. So I claim that this part here is a geometric series. So indeed, that is because if I look at the ratio, say 17 over 10 to the fifth over 17 to the 10 to the third, this ratio is simply 1 over 10 squared. And so this is the same as 17 over 10 to the seventh to 17 to 10 to the fifth. And so because this pattern will be continued in subsequent terms, I see that 1 over 100 is the R of this geometric series here. So it is also easy to see what the first term is. Well, it is the first term. It's written right here. So we're going to use that to denote, to compute the sum of the geometric series we have there. So our number can be represented as 2.3 plus the sum of the geometric series. Now, the reason we are doing it is we'll be able to replace an infinite decimal expansion with a finite, with a fraction. In fact, the sum of the geometric series is going to be a over 1 minus r. We have computed a, it is 17 over 10 to the third. That is divided by 1 minus r. So r from this computation here is 1 over 10 to the second. And so, great, we just now need to bring together these two terms, reduce them to the common denominator, and then we are ready to express the original decimal expansion as an irreducible fraction. Okay, so let's go ahead and do that. So first of all, let's multiply the numerator and denominator in this fraction by 10 to the third. So we can do that because for any fraction we can multiply its numerator and denominator by a fixed non-zero number that will not change the value of the fraction. So we have 2.3 plus 17 over 1000 minus 10. This is 2.3, which I'm going to write as 23 over 10 as a fraction as well, plus 17 over 900 and 90. You see that the common denominator is 990 because it divides both of the denominators here. So I will need to multiply 23 by 99 and add 17. Now I'm going to show you how to quickly multiply by 99. So it's as simple as multiply by 100 and subtract the number itself. Clearly it's the same value because multiplying by 100 and subtracting the number is the same as multiplying by 99. You just need to factor out the 23. And so it's this difference plus 17 divided by 990. And as a result, I have 2294 divided by 990. So this is a representation of the original number as a fraction, although it is not an irreducible fraction. It's easier to see that both the numerator and denominator are even, and so we can divide through by 2 at least. So let's go ahead and do that. So dividing through by 2 gives me 1147 in the numerator and 495 495 in the denominator. And this is incidentally an irreducible fraction. So either way, even if we stopped here, we would see that we can in fact represent a periodic decimal, a number with periodic decimal expansion as a rational number using the formula for the sum of a geometric series. So this is a quite remarkable fact. So now you know why it is that any number with periodic decimal representation is in fact rational number. And numbers such as e, pi, square root of 2, all of these, they have non-periodic decimal expansions. So if you look at their decimal digits, they are not periodic. There is no repetition as there was in this example here, of any length, not just of length. 2 digits, but of length 100 or a billion digits. You cannot find a period in the representation of, say, pi or square root 2. That is the difference between rational and irrational numbers.